Welcome back to Wireless Future. I'm Emil Björnsson, and as usual, this is going to be a conversation with Erik Larsson. Are you with me today?
Oh yes, hello Emil, how are you this morning?
I'm great. So I was thinking that today we're going to talk about machine learning. It's not that often that like engineering topics in general are being discussed in general media, but machine learning is always sort of popping up. Oh, now we have self-driving cars thanks to machine learning, or now we have new ways of identifying different types of diseases thanks to machine learning. So I was thinking that in this episode we're going to talk about machine learning and whether there are any application in the wireless area. So I think my first question to you, Erik, is what is machine learning, really?
Oh, what is machine learning? Wow, I mean, so again, this is a hype topic, right? I mean, it's everywhere in the daily conversation, even in the news. Machine learning and also artificial intelligence. And one way of answering would be to say, I mean, machine learning is when you do like linear regression and you have at least two data points, right? And artificial intelligence, if you have a computer program with at least one for loop and at least one if statement. But okay, getting more serious. I think in a nutshell, machine learning is about abstracting and extracting knowledge from data and then applying that data algorithmically to make inference and to make decisions, right? And artificial intelligence is like an umbrella that includes machine learning as one component, but also lots of other things. And I think it is probably a reasonable assessment to say that one of the reasons, or might be the main reason, that machine learning has become such a popular topic to talk about in the last 5, perhaps even 10 years, is the success of a specific category of algorithms known as deep learning and convolutional neural networks that have been immensely successful to applications, especially in computer vision, for recognizing objects in videos and pictures and such, and in natural language processing, in machine translation, for example, like Google Translate and that sort of applications, right? So, I mean, these applications and that specific technology of deep learning has been fueling, I think, a lot of the current interest or even hype that we're seeing in machine learning.
Yeah, and I think even when you're seeing a talk from people working in the wireless industry talking about machine learning, they often start with giving examples from like identification of images because it's so easy to see, okay, is there a cat or a dog in this particular image? And I think one way that I've seen also people describing it is like in the past, someone had to sort of suggest different features. So what is the description of a cat or what is the description of a dog? And then after we have defined that feature, we sort of write a computer program to identify and look for those features. But now with different type of learning approaches, we can also let the computer identify the feature in a better way than humans can do.
I think that's spot on the point. I mean, so now we're talking about a class of problems which are generally easy for humans, right? I mean, this is like a task that a 2-year-old can do, but it's very difficult for a computer through classical means because we don't have like mathematical models of what does a cat look like, or what does a dog look like, right? We can't describe like, well, the eyes have this shape here with this polynomial or something. We just don't have those tools, and that's, I think, the reason why these deep learning techniques have become so successful, and also the reason why we, in general, as humans, are so impressed by its performance.
Yeah, and is that really the computer's inability of doing it, or is it rather like we as a human know by heart how to identify, but it's very hard for us to sort of write down a specified list of how you identify a particular property. So it's sort of we who are the weakest link there in terms of writing that things down, tell the computer what to do.
Yeah, I think so. I mean, we have math that most or any of us can grasp, right, to describe what a circle looks like and what a straight line looks like, but not what a dog face or a cat looks like. So I think that's the point, yeah.
So when it comes to the more general term, perhaps data science, is this sort of related to artificial intelligence, machine learning as well, or is it a different topic?
Well, quite a bit. I mean, data science is about inferring information from big data sets, right? And it's essentially statistical inference. And then the question is, once you perform the statistical inference, what do you do with the information that you have gathered? Do you view it as you have learned something from the data that you can apply to making decisions or to other things? But definitely, I mean, that's another term that falls under this general umbrella of artificial intelligence and learning, right?
So is this machine learning topic something that is fairly new, or is it just that media have started to report about it?
It's not very new. I mean, a lot of the basics, ideas and algorithms go back decades. Even I remember I took a class back, I think that was in 1996 and 1997 as an exchange student in Aachen in Germany, and still remember this perceptron and this backpropagation learning with a gradient. So, I mean, these underpinning basic ideas of neural networks and deep learning are not new. Then obviously these algorithms have been refined a lot, and above all, we have gotten access to computing power orders of magnitude higher than we had 20 years ago. I mean, and we've also gotten access to data. We have, especially in these applications with language processing and image and computer vision, I mean, we have databases with millions of texts that the algorithms can be trained on, and millions of images and video clips that they can be trained on. So that is also obviously fueled here. I mean, the enormous computing power combined with the enormous availability of data, high resolution data as well. Yeah.
So you were mentioning deep learning earlier, and what is it that is deep, and what does it mean to learn something here?
Yeah, what is it that is deep? I think it's just that algorithmically, I mean, the algorithm has many layers, right? And what does it mean to learn? That's a good question. I mean, can an algorithm really learn anything? Hardly. I mean, at best it can approximate, right? It can approximate a function, which is very difficult to describe and which is highly nonlinear. And that's really what all these algorithms do, that they approximate functions. And they do that by fitting function to a huge cloud of points that come from the training data. I mean, that's mathematically really what this is all about.
Okay, so you sort of have some kind of training data that is specifying things you're going to observe. You know perhaps what you would like the function to output from those training data, and then from that you are training some kind of operation. Is this a neural network?
Oh, I mean, neural network is one specific, say, way of approximating functions, right? But in general, it is exactly as you described, that we have training data. So we have like a million of pictures, of half of them are cats and half of them are dogs. And then we run the algorithm and we tell the algorithm that, look, these are the dogs and these are the cats. And then we hope that the algorithm has approximated well enough a function, or air quotes, learned enough so that it can generalize, and the next time it sees a picture of a cat, which is slightly different from the training pictures, it can generalize and conclude that this is a cat and not a dog. Yeah.
I see. And I've heard about the universal approximation theorem. What is that one specifying?
So universal approximation theorem. This is a mathematical result that goes back decades. I mean, basically it states that you can approximate any nonlinear function arbitrarily well by using a deep neural network. And it is a mathematical theorem that falls in this class of like asymptotic approximation theorems, right? Which in themselves are not new. I mean, there's the Weierstrass theorem, for example, in calculus that states that, well, any continuous function on a compact interval you can approximate arbitrarily well in the supremum sense with a polynomial. So in a way, it tells us a lot. In a way, it tells us nothing, right? I mean, it's just a question: how deep has this network have to be, or how many coefficients do you need this polynomial to have to really give you a practically useful approximation? And that these theorems just don't tell us.
Yeah. So philosophically, it's sort of saying that we can do anything with deep learning, essentially, as long as we can specify the inputs in a mathematical way and the outputs in a mathematical way. There is a function that can take us from one to the other.
More
but
or less.
The challenge seems to be to actually find, not to say that it exists, but find it.
Yeah, right. And also, it doesn't tell us how much training data we actually need, right? And it doesn't tell us how deep this network has to be. And the deeper it is, I mean, the more you have to train it. So it just tells us asymptotically to increase the depth to infinity, then we can approximate better and better. But it doesn't tell us what does infinity mean. Is it 10 or 100 or a million or a trillion or something else? Yeah.
Yeah, and I think it's not necessarily the depth either that we need to make large. It could also be sort of the height, the number of inputs.
Sure.
It could be enough with one layer.
Yeah, the number of interconnects, that's what I meant, yeah.
So I think originally it was sort of about shallow learning, that we only had one layer, but it was large. And then we have seen that it's sort of, if you make it deeper, it's easier to get good approximations. So sort of also show how the original theorem is not telling us how to do things in practical manner.
Yeah, that's right. That's a more accurate statement, yeah.
And the learning procedure, that is some kind of optimization problem, is that right?
Yeah, essentially optimization. Essentially, I mean, it's like you have a nonlinear function with a huge number of coefficients that you need to select. And the way of selecting them is to optimize such that the function approximates your training data as well as possible. It's at heart, it's an optimization problem.
Yeah, and then this optimization problem, does it have nice properties so that we can find the global optimum to it, or?
Oh, wow. To my understanding, it doesn't. I mean, we can't even hope to find a global optimum. But as is the case in many engineering problems where optimization is involved, then we can at least find optima that are reasonably good, right? And maybe good enough for practical purposes.
Yeah, no, I think if you learn in mathematical classes how to find global optimum to functions and things like that, that is sort of applying to rather simple problems in reality, while these are highly non-convex problems that you can't really solve, but we're developing algorithm to look for local optima.
Yeah, somehow. Right, so you always look for local optima.
Yeah, and that might also be sort of a reason why this universal approximation theorem is more of a philosophical type of thing, because it exists, but can we find it? Probably not, because we cannot solve the optimization problems with million of parameters in reality.
Yeah, it's a good point. I mean, even if we knew that, well, there is a nonlinear function that does approximate our training data arbitrarily well, then, well, the question is still, how do we find it, right? I mean, as you said, it's a non-convex optimization problem. How do you find the coefficients of all these neurons and weights in the neural network? Computationally, really nightmare. I mean, as all non-convex optimization problems are.
But I think one of the interesting thing here is then that this is sort of involving so many different expertise, because the optimization itself is sort of a mathematical topic from the beginning. Then like learning approaches might be a data science or computer science area, and now it's also applied in so many different fields, and wireless communication might be one of the newest ones. So what do you think that we can use machine learning for in wireless communications?
So in wireless, I think there are cases where modern machine learning algorithms can help, and one is where we don't have a good physical model. And I think the prime example here is like whenever human behavior is involved, right? Suppose we want to model, for example, like traffic pattern or how we as humans move around in our house or in the city or somewhere, then we don't have like good tools to describe that. Well, obviously we could, use like Newton mechanics to tell, right? You can't accelerate arbitrarily fast and all that, but we don't have like good models for how somebody moves around in the city, say. So definitely, I think, their machine learning models could help, and based on seeing a lot of data, draw some conclusions or model what are like likely trajectories that folks like to move around, right? So when we don't have physical models, or good physical models at least. And another use case I can see is that for some algorithms, or some problems for which we know the optimal solution. The optimal solution is computationally very heavy. Might require like heavy belief propagation algorithms or Bayesian marginalization or Monte Carlo or something. And that there might be computational advantages in using technology that's being developed for deep learning, and specifically like even circuits that are specialized to implement neural networks, right? And these are highly power efficient and perhaps they could be just utilized like off the shelf as a building block and to approximate solutions that we know are optimal, but in a way that's computationally much more efficient.
Yeah, if I understood correctly, sort of the new iPhones and probably other phones have some kind of neural engine, I think Apple call it that, which is a small neural network where they can just import something into it, some weights and biases that are describing the neural network after the training, and then they use it to sort of, when you say Siri, then it knows that, now I shall listen to your voice or things like that.
Right. So I also heard that they have like an IP block that does neural network, right? And now given that we have access to this, then perhaps some components of established algorithms in say classical wireless comms could leverage those computational units. Now, it could be argued, I think, that that's not really learning, right? That's more like leveraging technology that's been developed for learning in a different domain, namely to simplify computational algorithms for something else, which is a legit use case, I think, but it's not really learning per se.
So I've heard about something, I think it's called deep unfolding, where you sort of, you take an algorithm that is iterating, and I think a lot of mathematical algorithms that we can show converges to some local or global optimum to something, they need many iterations to converge, and we only have proof that they converge asymptotically. And then the idea is then that you sort of say, okay, let's divide it up into different iteration. Let's represent each iteration by one layer in a neural network, and then we are sort of starting from that algorithm, and we let the neural network or learning algorithms improve on it. So it's sort of you add some trainable parameters to speed up convergence or something like that.
Right. Yeah, that's very clever. I mean, but is it learning? To me, that's more like tweaking of an iterative optimization algorithm.
Yeah.
So again, I mean, I think we have to distinguish here between algorithms or applications where we really learn something from data, and applications or use cases of this technology where we merely approximate some complicated nonlinear function for the purpose of simplifying computations or reducing the number of iterations you need in an algorithm or something.
But potentially the learning aspect here might be that if we have sort of an algorithm that can solve any problem of a certain type, but then we know that we're only going to use it on a smaller piece of all the conceivable problem of that type, then we can it's hard to specify what are the specific characteristics there, but if we are training it only on speeding up convergence on that subgroup of problems, then we are learning something from its structure in the
the question is how well does that generalizes then? I mean, once you throw data at the algorithm that the algorithm hasn't seen before, is it going to be as good as on the data that we trained it to use? Or is it going to be as good as the conventional solution? Or is it going to be worse? Nobody really, I mean, we can't know, right?
Yeah, and I think the word generalize that you mentioned there is very important, because it's sort of it builds on this idea that, okay, we have some training data, some observations, and in supervised learning we know what it should output, and in other types of learning approach we might not know it in the same way. But anyway, the hope is then that if you are later feeding a similar types of input that was not in the training data, but it's sort of generating similar way, then you will get an output that still makes sense. It's some kind of hope for interpolation between what you have seen before and what you will see in the future.
Yeah, so, I mean, the word, the key here, the point here is the word hope, right? So you hope that it will generalize, and we can't know. I mean, because we can't predict the future, so we don't know what data will the algorithm see in the future. We don't know what we as humans will see in the future, but we know even less like how will these algorithms react to what we could see in the future. So,
yeah, no, so that is sort of one of the weaknesses, I guess, of learning in general. That it sort of relies on some kind of craftsmanship on how you are teaching or training neural networks, and it builds on the hope and the experience that it does generalize rather well. But I think if you're going to train a car to drive by its own, then if it part of the time, not even if it just happens in 0.0001% of the time, something very stupid, it's very dangerous.
Yeah.
But maybe wireless have a sort of built-in reliability feature there, because we are used to retransmissions or outages and these type of things.
That's a good point. I mean, in wireless applications, we can never guarantee anything, right? It's always going to be outage, whether it's like 10% or 1% or 10 to the minus 5 or whatever, but we can never guarantee that information will reach the, whatever target destination we set, because of noise, because of interference, because of fading, and so on. And so in a way, we're a little more used to like the possibility of algorithm malfunction, and we can accept it if we have to accept it. It's just a limitation imposed by physics that it's going to be there. But if you build a self-driving car, then no, you probably don't want to accept like algorithmic glitches, right? That in some 0 point something percent of the cases, it just steers off the road or collides with somebody or something. We're never going to accept that. So that's a good point, yeah.
So now I've seen in the last few years that a lot of people are working or doing research on the topics of machine learning for communications. Is it possible to classify what type of research that people are conducting in those areas? What are good research directions?
Oh, I think you know more, Emil, but my understanding is that there are two categories here again, right? I mean, either we actually learn something for which we don't have a model. Like we learn like mobility patterns or something about propagation perhaps that we can't model, you know, physically accurately or even at all. So either we learn something for real, and I think that is legit to call this learning, or we merely approximate a nonlinear function, or we improve some optimization algorithm, or we replace some computationally difficult part in an algorithm with a nonlinear mapping that we can implement using a neural network circuit or IP block on a circuit. So I think that's really the main categorization here, right? Are we really doing like genuine learning from data, or are we applying some technology from the learning field to approximate complicated parts in complicated algorithms?
And the second part, you don't view that as learning in the same way?
Well, I think to me that's not really learning, right? I mean, that is more like computationally approximating difficult and complicated parts in an algorithm using technology that we borrow from the machine learning field.
Yeah, no, I'm starting to think about this analogy. Say that when you teach a kid to bike, and you tell them sort of the algorithm of how you're going to do it. Oh, you're going to turn your legs like this, and you're going to steer with your hands like this. And then eventually, when you learn it, it's difficult when you need to actively run this algorithm in your head. And focus on what you're doing. But when you have learned it so far, it goes back and it becomes some kind of automatic. That is when you actually have learned all of the shortcuts in the algorithm.
Right, yeah, perhaps, yeah.
Yeah, but I think when it comes to that first category of things where you don't have a model, I read about one interesting example where at the night the networks might not be used too much, or probably it's used at most in like at 10 a.m. or something like that when people are watching Netflix videos. But when people are actually going to sleep in the night, then you can start to turn off different types of network equipment, put them to sleep, and only turn them on when users getting active. And then you could try to learn in which cells can we do that, when if we start by turning things off, how often did we have to turn it on again, and sort of tweak those type of algorithms where it's hard to have a traffic model. Right.
Yeah, I think that's a great use case. I mean, this is spot on, right? Because here we don't have a physical model. We don't have a mathematical model that predicts that people are going to watch the Netflix at, I think you meant 10 p.m., right? No, hopefully not 10 a.m. But and we don't have a mathematical model that predicts that, but we could learn from data, obviously, and we could apply that learned knowledge to turn off the equipment when we know that with high probability it's not going to be needed, right? So we can save on electricity, power, and all that. I think that's a good example. And again, this is like well, it might be wireless comms, but it's more general. It's like data networks and information networks, right? How do we operate our data centers and servers and all the links in between them and so forth?
Yeah, and maybe that is sort of one of the important aspects that I can see this tendency of seeing that, if we can just replace everything with machine learning, everything would be better. But maybe it is sort of that we have been, as engineers, focused on specific small tasks, and we have given a model for that task. We have done a very good job on optimizing something. But then as we are putting together many tasks in the sequence, then there are optimization learning approaches in between the different tasks. And in cases where our models were bad, then we can also do better.
Yeah, I think that's a valid point. I mean, it goes back to like 20 years ago, this was known as cross-layer optimization, right? Where you wanted to optimize like physical layer and wireless jointly with the MAC layer, jointly with perhaps on the application layer. And maybe now we can do it for real, because it might be more important to actually have an algorithm that can learn when people are likely to be asleep, so we can save power, rather than saving like 1% of transmission power on the physical layer. And here I think learning definitely can play a role. So yeah, that's a good point.
So if we look further into the future, do you think that sort of machine learning based algorithms will replace everything that we are using in wireless systems, or is it sort of a complement, an add-on to what we already have?
Yeah, hardly replace everything. I mean, no, I don't think so. I mean, here's the thing, right? There are lots of problems in wireless comms, especially in the physical layer, for which we know the optimal solution and have known the optimal solution for like 20 years. Or extremely close to the optimal solution at least, and where there are extremely power efficient implementations already available. So why would we do anything else? I mean, it makes hardly no sense. As a complement, definitely. I mean, as I said, there are problems where we don't have good models. There are algorithms still that are computationally very heavy and therefore power hungry when you implement them on silicon, and where certain parts could be replaced by optimized nonlinear mappings that we borrow from the machine learning technology. And there are a couple of scattered problems as well. I think modulation recognition in wireless is a fairly good example, where deep learning and machine learning based algorithms just simply outperforms. I mean, the kind of conventional style approach to the problem, which would be like, well, Bayesian map or something, which we know is optimal, right? But it's just computationally nightmarish to work with, and where best in the market algorithms are based on machine learning. So definitely as a complement, I mean, I think it is an important tool that we all ought to learn and to be good users of. It's there and it's going to be there. There's no question. Yeah.
Yeah, so I think right now the International Telecommunications Union, or ITU, they are putting together a series of different competitions where they like to train engineers to apply machine learning and communication. And I put together a team with people from Linköping University and Lund University that was competing in a challenge that was about like some very classical things, channel estimation with beamforming, hybrid architectures and things like that. And sort of the task was that, okay, you get data for one particular propagation environment and now you can learn specific features. We don't know the model for it, but there is some kind of underlying physical model. So we try to learn things like that. And I think... not to brag, our team came on second place, but I think the outcome was sort of that the first three approaches that in that competition was all based on combining traditional knowledge with some trainable aspects to it, to sort of try to learn some parameters and then apply traditional estimation methods, for example, while methods that was only based on trying to learn everything from start to end didn't perform as well as these type of things. And I like to tell my students as well that if you're going to train a car to drive on the road, you don't let it start to discover what a wheel is and what it means to drive and what the road is. You sort of try to inject everything we know and then start from that and do something better.
Yeah, I think that's the point. I mean, not neglect all the experience and model knowledge and knowledge of the physics that we actually have, but rather leverage that and build perhaps machine learning algorithms on top of that knowledge. I mean, they can learn, as you said, in a specific environment, and I'm sure you can do better. I mean, obviously, this is always true, right? The more prior information you inject, the better you can do. This is true in statistical inference, it's true in decision making, it's true across the board. So obviously in wireless as well. And then I think the real issue is how well does this generalize, right? I mean, you could train your algorithm I have an access point in the room I'm sitting here. And we can train this algorithm that most of the time I'm in this corner, and some of the time the door is open, some of the time the window is open, and so forth. But the issue is really, now what if we take this access point and now move it to a different room or somewhere else? Will it perform as well? Do we need to retrain? How much do we need to retrain? How robust will it be? So the gains that we got, are those will those be counterbalanced, or will there be a loss somewhere else? So it is always, in a way, it's a matter of how much prior knowledge do you inject. And you can inject this either through classical means. You do Bayesian inference, right? You always have a prior. Or you can inject them through training, by training your algorithm in a specific environment. And obviously, it's going to work better in that environment when you trained it. But the question still is, how well is it going to do when you put it somewhere else? So anyways, yeah.
Yeah. So I guess in many cases, it's really about that you are narrowing down the applicability of your algorithms, and you learn something that's specific for the location, the context where you're going to use your algorithm, and that is where you are squeezing out the additional benefits. So maybe there are some undergraduate or graduate students now that they'll listen to our podcast, hopefully. What do you think, what should people learn in general in school in order to be good communication engineers in the future? Is it mainly machine learning today?
To be good communication engineers, I think, number one, you should learn math. Number two, you should learn physics. Number three, you should learn the basics, the foundations of comms, right? Physical and Mac layer especially. And then in your toolbox, you should you should learn machine learning as well as one tool in the toolbox. There's no question. And I think it's also important to stress the fact that machine learning is not limited to deep learning and neural networks, just because those have been hot in the last 5 or maybe 10 years. But machine learning is a whole portfolio of other techniques that are also highly useful and that we should also teach. So I definitely think, this is one tool in the toolbox, one class in the curriculum, just like students learn optimization. They should also learn machine learning, right? I think that's my view on that.
Yeah, no, I certainly agree. Machine learning, optimization theory, Fourier analysis,
probability,
you can make a list
statistical
of things.
Inference.
Probability, yeah.
Yeah, classical detection estimation theory, right? Which is, in fact, immensely useful on problems where we have good models. So let's not forget that.
Yeah, no, and I try to tell this to undergraduate students as well, that don't focus entirely on machine learning, because as we were talking about earlier, you need to sort of have this mix of expert knowledge from the past with a combination of machine learning to do good things, because you cannot start from only using machine learning. So it's very important to have that type of mix. And I heard examples where companies are sort of creating additional deep learning or machine learning division that is going to do something productive, but now they realize it's better to spread those people out over the company instead.
Yeah. Again, it's a tool in the toolbox, right? And I heard some horror stories, like a colleague of mine had been on the examination panel of a master thesis, and the student had implemented a neural network to detect the signal in noise. And my colleague asked, so did you compare to a likelihood ratio test? And the student had no idea, and the advisor had no idea either. And this is like the optimal solution known since the 60s, right? Or even more longer back. So I think, let's not forget, we need to, now speaking of education, we need to teach the fundamentals, right? We need to teach physical modeling, we need to teach statistics, Bayesian inference, detection estimation theory, and so forth. And then we have those as baselines, and these are highly useful techniques. And then we teach machine learning as another tool in the toolbox that we can apply when we don't have good models, or where the classical conventional algorithms just aren't feasible or aren't applicable or just computationally heavy. So I think that's probably the yeah.
So when it comes to this model efficiency and algorithmic deficiency that we talked about before, is it to sort of deal with that by using machine learning type of methods? Is that just a sign of laziness that we didn't want to spend the time on try to improve our algorithm instead in a controllable manner or improve our models? Or is it a sound approach to deal with deficiencies that exist?
I think both. I mean, there might be scenarios where we just don't have models, right? I mean, there are definitely scenarios where we have good models, Newton mechanics, Maxwell's equation, wave propagation, and so forth. But again, we were on this earlier, right? There are situations where we just don't have physical models. How does a human move around in the city, for example? And so I think, to your question, I mean both. At part there might be model deficiency and at part algorithmic deficiency. We just don't know how to, it's just computationally too hard.
So do you have any concrete example of things that people have done in the literature when it comes to machine learning for communication?
I mean, I've seen lots of papers, right? Because it's been like a popular topic in the last few years. And one thing I've seen people doing is like to replace like an end-to-end physical layer communication link with something that's air quotes learned or trained, where the idea is then that, at best this machine learning or neural network algorithm would rediscover that you can use signal constellations and you can use like a Hamming code or something. But I guess that could be like a fun exercise if you teach this topic. I don't know, but it's hard to see why it would be any much of useful. And what else? I've also seen like papers where machine learning is used to replace certain optimization algorithms. Again, that might partly make sense. One can question to what extent this is really learning, because these algorithms are trained on the optimal solution that has to be found by other means, right? But it's possible that in some cases, finding the conventional optimization algorithms are just too heavy, and somebody's neural network can do a quick and dirty job and get an approximate solution fast, right? The issues I have with now, I think you know more, Emil. I just followed partly the literature, but one of the issues I have with the work I've seen is that none of this scales, right? It's scalability. You increase like the dimensions of your problem a little bit and you hit the wall. So it is not immediately obvious how useful it is in the end. I'm sure we have more examples.
Yeah, no, I think it's sort of one of multiple tools in order to try to improve on things. And it might be a good way of exploring, is there some additional model deficiencies that we haven't thought about before? So when it comes to the end-to-end learning, what could we do better compared to what we do today? If we are building the system like we are used to, we send some known signals to learn the channel, and after that we are sending data with a particular constellation. Could we do better than that somehow? And then of course the problem with learning approaches is to always find a suboptimal solution. But if that suboptimal solution is better than what you have today, then that shows that there is some possibilities of making improvements in the future.
Well, it's all a computational problem, right? If you talk about like transmission on a wireless physical layer, then the conventional approach is to send demodulation pilots so that the receiver can estimate a channel and then use these estimates in the demodulator. Now, there's nothing really in comms theory that stipulates that we need pilots. In fact, we can just transmit the data and we can run the map detector, which we know is provably optimum in a minimum probability of error sense, right? The issue is that this map detector, just the way if you just write it up straight up on with Bayesian analysis on the board, is computationally, if not infeasible, it's at least very, very heavy to run. And sure, it's possible that machine learning or the sort of learning algorithms could help there, but is that learning? Hardly. Again, this is a computational approximation of something that we know is optimal and is done in a different and quick and dirty way. So it's possible.
Yes, so I guess what we are learning is the shortcut and how to what part of the existing algorithm that we can throw out and which one are essential in order for it to speed up.
Yeah, right. Again, mostly it's about speeding up computations, right, through approximations, and technology from learning there could very well help. Because again, learning is very much about finding nonlinear functions that approximate some input-output relation.
So one thing that I've been working slightly with is hardware imperfections, where you sort of have non-linear behaviors, and I think we talked about that in previous episodes as well, that in power amplifiers you have non-linear behaviors, and there are definitely conventional models for that, but even if you have a model, you need to sort of try to estimate certain parameters in that model, and then you're going to use those imperfect estimates to do something to counteract them, and I was trying to sort of deal with the whole thing at once instead of putting up a model, estimating parameters. We try to counteract the entire thing with one neural network. Is that learning to you?
Slightly more so, perhaps, because still, at least here you have like some phenomenon, right? Like a nonlinearity that you might not have a priori a good mathematical model for, or even have a good parameterization of. So in a way, I mean, the algorithm learns perhaps then what its nonlinear characteristics looks like. I'm sure this will work, I mean, and then the question is, of course, always what is the baseline we compare against, right? I mean, is it the optimal Bayesian detector and where you parameterize this unknown nonlinearity through some polynomial or whatever function with coefficients you marginalize over and so forth. I think it's a good use case. I mean, let's not forget that the main issue with nonlinearities in power amplifiers is the generation of spurious out-of-band emissions, right? And machine learning is not going to do away with that, I think. But if you just look in-band, then you'll have a little bit of signal distortion, which is nonlinear, and which is traditionally quite difficult to model. I mean, you need like Volterra series and lots of complicated mathematics, and I'm sure that learning could offer like a shortcut to perhaps doing all that math and having complicated algorithms to identify all these coefficients in the Volterra and all that. Yeah.
So maybe our listeners now get the impression that we are very skeptical against what the prospects are of getting any gain. So do you have any good examples or good use cases or ideas of where it's going to be used well in the future?
Well, I mean, I'm returning to this point, right? Higher layers where we have traffic patterns and human mobility and other things involved that we can't model through physics at all. We just don't have any tools, any mathematical tools to model rigorously how people behave or like that. On a physical layer, I think you probably can squeeze a few percent. Now, whether that's important or not, I'm not sure. But you probably can do it. You probably can squeeze computational efficiency in some cases. Whether that's important or not can be debated. But I think the main promise that I see is, again, on high, maybe Mac, but definitely Mac and above, I mean, in comms.
Yeah, no, so in the physical layer, my impression is that as long as you know the channels very well, we know how to solve the problem. That is what people have been dealing with for ages now. And therefore, it could be complexity issues with applying those algorithms that could be improving, make it possible to implement certain algorithms in reality that we haven't been able to do before. And then when it comes to sort of model efficiency, yeah, we can squeeze out some things when it comes to how to learn the channels more effectively. But at the end of the day, we are maybe spending 5 to 10% of our signaling on learning the channels. So that is the gain you can get if you get rid of that. That's 5 to 10%.
Is that a lot? 5%? I mean, I don't think so. It's hardly anything to jump high over, right? I mean, if you compare to other technologies that really made a difference, if you compare to like massive MIMO, we speak of improvements in 10 or 100 times, then is 5% a lot? Not really. But I think returning to your point here with pilots and channel state information and all that, I mean, channel state information, and specifically the accuracy of the channel state information that we have, tends to be the limiting factor in wireless, right? And then we have to remember that two kinds of channel state information here. Number one is at the receiver, when you demodulate your data. And that channel state information in principle you can do away with by using more advanced receiver algorithms. You could use learning. I'm sure you could use learning, but you can also use technology that's been well established and tested like 20 years ago with iterative detection, decoding, demodulation, where you feed soft information between your channel code and your demodulator and your channel estimator and so on. And the improvements here are marginal at best, I think, in terms of, how much you can save, right? Because these pilot resources we're talking about are like a few percent of the overall signaling, so it's hardly a big deal. The other case or situation where channel state information is critical is at the transmitter, and especially when you have multi-antenna systems like MIMO or massive MIMO, right, where the transmitter has to know the channel state information to beamform, to make sure that information reaches the intended terminals and that it doesn't interfere too much with other terminals. And that is a tougher deal, and here the signaling overhead associated with actually getting that channel state information is much higher. So, well, if we do anything there, but again, I mean, it comes down to how much prior information you inject in your algorithms. How much do you teach your algorithms or tell them about what the propagation environment looks like? So, yeah, possibly, I mean, learning could help there to some extent.
Yeah, so I guess at the physical layer is really that we are narrowing down the use case of different algorithms and methods to a specific environment where we can inject some knowledge and learn this type of knowledge. Yeah. But I certainly agree that it is at higher layers where I also see the largest improvements, things like load balancing or for the operation of the network. If you can load balance in a better way between your cells, or if you can... I heard that 1 decibel of SNR is worth $1 million or $1 billion or something like that.
Depends on whom you ask. I mean, back in the deep space communications area, I heard a number of $80 million per decibel, but I suppose it depends on what exact year you were referring to. And
so even if the communication performance is not improved very much, if you can remove a few base stations or not densify in the same way and have a better management of your resources, that could save a lot of money on that side.
Potentially, But I think here's another thing. So we talked about algorithms that could learn, right? About the propagation environment and so forth. And obviously, if you know something about your propagation environment, like the channel covariance or whatever knowledge you have of it, you can do better. That's clear. But let's not forget that if we take the single most successful technology, that's the foundation of 5G, massive MIMO, then one of the main selling points of massive MIMO, it works now in reciprocity-based mode then. It works without any prior assumptions, essentially, on the propagation, right? So it's exceedingly robust in that sense. And I'm sure you can do better if you inject prior knowledge, for example, through a trained machine learning algorithm. But the question is, where is the cost, right? I mean, you train the algorithm to work perfectly well in this room here, and then you move the access point to upstairs or somewhere else. Then is it going to work at all, or is it going to work even as well as the baseline does, or is it going to be worse? See, this is the point, right? I mean, there's always a trade-off between how much priors you put in and the performance you get. And you probably want technology that is robust and doesn't require a lot of priors at all to function. So let's not forget that point, I think.
Yeah, no, I think that we shouldn't expect that we can offline train something that we're going to be used on every base station forever, but it's rather that we're going to train it for each access point separately to learn some local characteristics there, and if we are moving it, we will need to retrain it, and we might even have to continuously improve the learning and adapt to changes because the weather is changing, or different people are moving around. People start to work in their homes instead of the offices all of a sudden.
And that happened instantly, right? It happened overnight when the COVID pandemic struck. So then these algorithms have to react fast as well to detect the change, I think,
So is there a tendency that we are replacing knowledge and with computing power somehow, that we just throw a lot of computing power on all of our problems and don't try to learn anything ourselves?
I hate to be the pessimist in the room now, perhaps, but I think so to some extent, right? I mean, a good example is the one I alluded to earlier, right, with this detection of a signal in noise, where you could apply a generalized likelihood rate to a test from the 60s, and that it's if it's not optimum, it's very, very close to optimum at least. Well, it'd be easy to ignore all that knowledge and insight and just throw a neural network at it and play with the parameters and tune the ReLU functions and all that, and it's going to work. But is this a good solution? I mean, to me, it really goes against the main, the point in philosophy of science, the Occam's razor, right? We're looking as scientists and hopefully as engineers always for the simplest explanation, the simplest possible explanation that's consistent with observation. So we want, insofar as possible, we want clean and simple mathematical models for which we can prove optimality of certain algorithms and certain inference and so forth, rather than just throwing a supercomputer at the data and hope that anything useful will come out. So I do think that we have to be a little concerned here, and I think especially that we need to be careful with the, say, next generation of students that we educate, that machine learning has to be there. Obviously, it's a tool in the toolbox, right? But let's not forget all the classical math and physics and statistical inference and Bayesian inference and all that, which is in many cases extremely good and quite simple and probably optimum.
Yeah, and I think that I chose to work in academia for the reason that you should have the time to work for a year or two on really understanding a problem and do it the best as you can. But for the industry, we have this concept of technical debt, where you know that a solution that you were putting in to reach a deadline was quick and dirty. And hopefully you could deal with the dirtiness later on. But if it builds up, this becomes very hard to deal with. And if you throw machine learning into there and do something that it just works, but you don't know why, and you can get weird effects.
See, that's the point. I mean, we might be educating a generation of engineers who knows how to get certain things done, right? I mean, you open Python, you import TensorFlow, and then you throw data at the problem, but who have no idea why it works or why it doesn't work, or when it goes wrong, then why does it go wrong? And think of it, I mean, this might be okay if we work with like entertainment applications, right? I mean, if your video game just has a glitch, then who cares? But if a nuclear power plant has a glitch, then bad luck. I mean, so I think we need to build resilient engineering systems and that are also understandable. And the only way of making them understandable is to build them to rely on models that we as humans can understand well. And that means, in many cases, I mean, physical models, perhaps rather simple physical models, and classical inference.
Okay, so before we wrap up, we could just elaborate a little bit more on some of these more general issues that are brought up when it comes to machine learning. So is machine learning taking our jobs?
I don't think so. I mean, that's a point that's being repeated over and over again, right? I think it's mostly nonsense. If this were true, then machines would have taken our jobs long ago, even, I mean, at the start of the Industrial Revolution. That never happened. So I think it's just that, well, some people might work with other things, but AI and machine learning is not going to take our jobs. I don't think so.
Yeah, no, when I was buying my doctoral hat, I saw an article said from hat maker to app maker. That was sort of describing how certain professions are disappearing and others are appearing. And there might be many more app makers today than hat makers.
Yeah.
Yeah, and this lack of interpretability is something that I guess we have already touched upon.
Yeah, that one I think is important, and I think it's a potential threat again. I mean, as I said, we are, the risk here is that we are educating a generation of students who just like to import TensorFlow and throw data at the problem rather than really understanding the physics behind and understanding and applying classical and probably optimal inference algorithms. So I think that's something we have to be careful with here, really. And again, it all goes back to philosophy of science, right? And the Occam's razor. They were looking for the simplest possible explanation that's consistent with observations of the physical reality. And classical physics and inference and math offers that, but machine learning hardly doesn't. So, yeah.
So I like to tell my students as well that okay, we have an existing solution, we're going to beat it with machine learning, and then we're going to go back and try to improve our algorithms that we can explain and view it more as a tool to move forward and discover where there is possibility of making things better or not.
Yeah, right.
So my last question then to you, are there any new security threats that is created due to machine learning?
So this depends on what you weigh into the word security, right? I mean, there is for sure a lot of talking about algorithms, machine learning algorithms being biased in the inference that they make, and that would be a problem. I think this is largely a gimmick. In fact, all inference is biased, right? I mean, classical Bayesian inference, you have a prior. The only difference is that in Bayesian inference, you declare your prior, so everyone can see it and inspect it. In machine learning, well, then you might train more on a certain type of data than other type of data. That's going to give you some sort of air quotes bias. I don't quite like the name because, it's like nothing is unbiased, right? The question is rather, is it going to be your bias or is it going to be my bias that decides? The other thing is on...
I guess that is saying that it's important to find the right type of training data, that one is representing what you're going to do. And then in communications, it might not be as problematic as in cases where people are misclassified because of their race or gender or something like that, because the training data was biased in a particular way.
Yeah, again, so... other security threats. I mean, one thing is that some of these algorithms for machine learning and like object recognition, for example, in computer vision, are highly susceptible to small crafted perturbations, right? So you could take, this is classical example of a computer vision algorithm that's supposed to recognize road signs, and it was trained to recognize stop signs and speed limits and so forth, and then we're just perturbing slightly the way the stop sign looks. I think what they did was to put like a stripe of tape on it, and that caused the algorithm to misclassify the stop sign as a speed limit instead, which obviously is a disaster if you if the algorithm feeds the algorithm in a self-driving car, right? And the point here is that you can't use just any stripe of tape or any way of perturbation of the image, but you have to craft it very carefully. So you have to optimize exactly where you put this stripe of type in order for the algorithm to make this foolish mistake. And it's possible. I mean, I think we have to be aware of this threat, and it could potentially be exploited. I think we have to be aware of it, and we have to find countermeasures. So that's important. So that might be one security threat that's really emerging here.
Yeah, I guess it both these kind of jamming issues that we talked about before, if we are sort of learning how to estimate channels and things like that and exploiting the propagation environment, then we might be even more susceptible to jamming. And if you sort of have higher layer approaches where you try to learn about the traffic, then someone could potentially put up a lot of small emitters in their home to sort of get the network to believe that, most of the traffic is coming from this direction, so we're going to rotate all our beamforming here most of the time, and then you get better coverage at the expense of someone else.
Right. On the other hand, I'm not sure that machine learning approaches are more susceptible in that specific application than any classical algorithm would be, right? I mean, wireless as such is highly vulnerable to all sorts of attacks on the physical layer. You can easily jam a wireless base station just by brute force, just blasting RF power at it. So it's not immediately obvious to what extent. I mean, it is true that the use of machine learning techniques introduces new types of threat in this domain, but it's not immediately clear how large are those threats relative to other threats that we already have to face.
Okay, so I think we are reaching the end of our conversation about machine learning and communication, and we will be delighted to hear your feedback and thoughts around this, so please leave a comment or send us an email. And thank you for listening to this episode.
Thank you.